Hello, am I audible? Hello, am I audible? Thank you, Kunal. Okay, thank you, Gargi. Allow me to show my screen. What you see on the board is what we had discussed, what we had started discussing about Exergy. I would be repeating it because we had a break. Just in case you had forgotten what we were discussing, I'll do a quick revision before I move to the next concept. Okay, so this is the plan of today's lecture. So in order to test whether you have really followed what was discussed, let me ask you one question and I'll be writing that question on the board. Okay. You can solve this and write your answers along with your name. Okay. In the questions column. Okay. So that allow me to write the question. I'm penning the question on the board now. Okay. So I am interested in finding, let us say, the exergy. Find the exergy or available energy. Find the exergy or available energy of the heat Okay. Find the exergy or available energy of the heat find the exergy or available energy of let us say of 1000 kilojoules of heat of 1000 kilojoules of heat, okay, available from the source which is at let me erase this. Erase it. Okay. Source which is at 1000 Kelvin. Okay, 1000 Kelvin. Okay, and let us say that the ambient means surrounding temperature is, let us say 27 degrees centigrade. Okay, so I want you to calculate the available energy or exergy. This is just to is sort of revision of the concepts which you have done, and I want to ensure that you have internalized those concepts. Okay, so I am interested in finding the available energy of the heat, okay, of the heat which is being supplied by the source, and the source is at 1000 Kelvin. The source is at 1000 Kelvin, and this heat is being supplied. The quantity of that heat is given to be 1000 kilojoules. I'm interested in finding the available energy or exergy of this heat. Okay, so tell me what is the exergy or available energy. Tell me the exergy or available energy, and how do we calculate that? Okay, how do we calculate that? I'm waiting for your responses before I explain the concept again. Any answers? Okay, Kunal has given some answer. Kunal and Gargi. Anybody else? Apart from Kunal and Gargi, I want others also to answer. Okay, Gargi has given some formula. Tejas is writing some formula. I want the answer, Tejas. Tejas Sanap. Nikhil Pardeshi has given some answer. Nikhil, Tejas, Kunal, Gargi. Anybody else in the class? Okay. So let me explain this because I feel that very few students are answering this. This was already explained to you. Formula is right, Gargi, but we need to explain this to the class once again, I guess. So allow me to explain this. How do we calculate? Okay. Okay. So only few students have answered: Nikhil, Tejas, Gargi, Kunal, etc. So how do you calculate this? So we need to, in order to calculate the available energy or exergy, we need to do a thought exercise. What is the thought exercise we need to do? Any answers? We need to do a thought exercise if I want to calculate the available energy of the heat. So what thought exercise we need to do? We need to assume something, right? If I want to calculate the exergy, we need to do a thought exercise. So what is the thought exercise we need to do? Because exergy is the maximum work potential, so we need to, no, that is not the thought exercise we need to do, Gargi. That is not that answer. We need to assume, okay, we need to assume that if I want to calculate the exergy of heat, okay, which is available at certain temperature, then we need to do a thought exercise. Means we need to assume that that heat is supplied to a Carnot engine. That heat is supplied reversibly. That heat is supplied reversibly to the Carnot engine. Okay, and then we calculate the work output from that Carnot engine. Okay, so the thought exercise we need to do is that we need to assume that that heat goes to a Carnot engine, okay, reversibly, and the Carnot engine produces work. And then in that case, and the Carnot engine rejects the heat to the dead state temperature, right? And the work output of that Carnot engine is then the exergy or available energy. Okay, so let me draw this. What thought exercise we need to do? I will choose a different color for that. Okay. So the thought exercise we need in order to calculate exergy. Okay, to calculate exergy, right? For this heat, to calculate exergy, what we need to do is that we need to think of the heat which is available from the source, which is at given at 1000 Kelvin, is supplied. Okay, it is assumed that this heat is supplied reversibly to a Carnot engine, and this Carnot engine would reject the heat, would reject certain heat, okay, to the surroundings, which is at the ambient temperature, okay, dead state temperature. Okay, so it is given in this problem that the dead state temperature is 27 degrees centigrade. So 27 plus 273 is 300 Kelvin. Okay, the source is given to be at 1000 Kelvin, and the heat which is supplied is also given to be the heat whose exergy is to be found is given to be 1000 kilojoules. Okay, so the thought exercise is that this heat is supplied to a fictitious engine, a Carnot engine, and this work output of this Carnot engine, which would be the maximum work output, okay, this would be the exergy of the heat supply. This is the exergy of the heat supply. And what would be the work maximum? That work maximum is nothing but the efficiency of the Carnot engine, conversion efficiency of the Carnot engine, conversion of heat to work efficiency, that is the Carnot efficiency into heat, which is nothing but 1 minus T naught by T into Q. 1 minus T naught by T into Q. And in our case, this is 1 minus T naught is 300 and T is 1000. Let me write it somewhere else. I'm writing it here. Okay. So 1 minus T naught is 300 and T is 1000 into Q is 1000. So this is 700 kilojoules. Okay. So the thought exercise we need to do to calculate exergy is that we need to assume that the heat, okay, whose exergy is to be found out is supplied to a Carnot engine which operates between the source temperature and dead state temperature, and the work output of that Carnot engine is then the available energy or exergy. Okay, yes or no? Is this understood now? I hope this is clear to you. Okay, so the answer is the available energy of 1000 kilojoules of heat, which is at 1000 Kelvin, okay, is equal to 700 kilojoules, okay, right? Now I want you to show this 700 kilojoules on a temperature entropy diagram. Okay, I want you to show this 700 kilojoules on a temperature entropy diagram. So how should I represent this 700 kilojoules on a temperature entropy diagram? So let me use another page, okay, and another pen. So in order to represent, okay, exergy representation, in this case, how would be the exergy representation? So this exergy can be represented on a temperature entropy diagram. Okay, first I would represent the heat supply. So represent the heat supply. How much is the heat supplied? Represent the heat supplied, the heat on the temperature entropy diagram. Okay, which is at 1000 Kelvin. 1000 Kelvin. So the heat supplied would be, so suppose this is 1000 Kelvin. So suppose this is 1000 Kelvin. So the heat supplied would be this portion which I had drawn. Okay. This hatched area, shown by yellow, this hatched area is the heat supply. This is the heat supply. Okay, this is the heat supply. Okay, now I want you to show the unavailable energy on this TS diagram. Unavailable energy on the TS diagram. Unavailable energy on TS diagram for this given problem. Okay, for this given problem. So the unavailable energy on the TS diagram, okay, would be I'm using the red pen for that. Let me use some other pen. Okay, I'm using the red pen now for showing the unavailable energy. So for showing the unavailable energy, I need to show the dead state temperature. So 300 Kelvin is the dead state temperature which is given. Okay, and the rectangle which is shown by red, now, this rectangle. Okay, and with the vertical line, this rectangle is the unavailable energy. So calculate the unavailable energy and tell me the answer. What is the unavailable energy? You tell me the answer. What is the unavailable energy? You tell me the answer. No, that is not the unavailable energy. What is the unavailable energy? Gargi, your answer is wrong. What is the unavailable energy? You tell me the answer. Yeah, Kunal is right. So if you look at the diagram, okay, let me explain you this. Only one or two students. Yes, Ganesh is right. So look at this. Gargi is right. No, Gargi, 300 kilojoules is not available energy. Gargi, you are making some mistake. See, unavailable energy would be what? Unavailable energy would be, see, you are supplying 100 kilojoules. Okay, let me go to the initial diagram. See, on the board, you see the area ABCD. Let me just finish this diagram. Okay, I will call this as EF. Okay, area ABCD is the available energy. Area CEFD or CDFE, whatever you want. The area CEFD is the unavailable energy. Okay, and the area ABEF is the heat supplied area. If you have understood this diagram, then it should be very clear to you. Again, I will repeat. Look at this diagram. The area ABEF, that is the area under A to B. I'll be using other pen now, other color. Let me use a green. Okay, just to highlight the area under A to B. That is this area. This total area under A to B means area ABEF. That is the area ABEF this area is the heat which is supplied. Okay, this is the heat which we are talking about, whose exergy is to be found out. This is the heat whose exergy is to be found out. That is A, B, E, F, right? Now, of this A, B, E, F, not all the heat is exergy. Not all the heat is available energy. Then how much is the available energy? The available energy would be the area A, B, C, D. Okay. So the area exergy, the exergy would be, or the available energy would be, the available energy or exergy would be the area A, B, C, D. The area A, B, C, D is the available energy or exergy. So if I use a green pen for showing available energy, this is the available energy. So the green hatched area is the available energy. Now, obviously, if Q is the available energy, Q is the heat supplied, and of this Q, available energy is AE. Okay, available energy is AE. Then Q minus AE is the unavailable part. Okay, so the heat under consideration can be thought of as like this. So of this heat, some of the heat is available, that is available energy, and the remaining part is unavailable energy, right? So, or you can use other term of this heat, some of the heat is the exergy, and the remaining is the energy, which is not available, energy. Okay, right? Not energy, ANERGY. Okay, or AE plus UE, available energy plus unavailable energy, is the heat supplied. So if you look at it from the on the TS plane, if you look at the representation of available energy and unavailable energy, it becomes clear to you that the area of this rectangle A, B, C, D, which is nothing but the work output. The area of the rectangle A, B, C, D is what? It is nothing but the work output of the Carnot engine. This is nothing but the work output of the Carnot engine, W max. Okay, W max. This is the available energy. Provided this temperature Tc is equal to Td is the dead state temperature. Provided the temperature Tc is equal to Td is the dead state temperature. Okay, and the area under the dead state temperature line. Suppose the dead state temperature is T0. So the area under T0, is the unavailable energy. Okay. So the Exergy equation or the available energy equation becomes like this: AE is equal to heat, which is Q, which is nothing but the area ABEF. This Q is the area ABEF minus T naught delta S. Means what? Area T naught delta is what? Area DCEF or CDEF, whatever you like. Okay, area CDF, and this addition of the two, and this AE, available energy, is area ABCD. I hope this is clear to you. Neha, you need to correct your answer now. Neha, so what would be the correct answer, Neha, for the problem, given problem? Neha Aire, tell me the correct answer now. If you have followed this discussion, tell me the correct answer. Nikhil, Tejas, yeah, Gargi has followed this now. Neha, can you tell the answer? Ganesh has already understood this. Nikhil Pardesi, anybody? Okay, it is not that only few students should answer. The entire class, I see around 120 plus students are attending this class. Okay, so I am expecting that others should also try to answer it. It is not a very difficult concept. Okay, you need to just pause a bit. Okay, think a bit, right? Revise a bit. You are also given videos for revision. Okay, so I want all of you to understand this. And I'm purposely going slow so that you internalize this very interesting concept. This is very interesting concept. Okay. So anybody else who wants to answer this question? What is the unavailable energy? Yes, yes, correct. Energy means unavailable energy. I'm using a different term. So energy is unavailable energy. Right, got it. Anybody who wants to answer this question, what is the unavailable energy? Neha, you want to revise your answer? Neha, Aire, Rushali, Yashmore, Yugandhara, Vivek Chaudhary, Vedant, Varun, Utkarsh, Tejas Patil, Tanaya, Sushant Kanade, Siddhil Jadhav, Shubham Hande. Any answers you have? What is the unavailable energy? Okay, so let me move ahead now. I assume, okay, Nikhil has correctly answered now. Nikhil, you have understood, I guess. Others, Shubham Hande, Shantanu Dharmadhikari, Shifan Pathan, Shreyas, Selva Rajin, Satyaprakash Parida, Saurabh Bakre, Sanket Jadhav, Samir Patil, Rutvik Patil, so many Patils are there here, Roshan Jadhav, Raju, Purva, Prathamesh, Pranjal, Pranav, Pooja Awad, Nitin Patil, so many. Neha, have you got the answer, Neha? All right. I assume that you understood. Okay, and let me go ahead with the related topic, that is the decrease in unavailable energy. Okay, so the answer is, the answer, as I told you, for this problem is the available energy is 700 kilojoules and unavailable energy is 300 kilojoules. Okay, now I'm moving to the next part, that is, let me use the red pen now again. So I would now come to the concept of decrease in available energy. Decrease in available energy due to irreversibility. Due to irreversibility. To understand that, we had a lot of discussion on irreversibility. Okay, so we said that the second law of thermodynamics, okay, points out that a reversible process is an ideal process and all the actual processes are irreversible processes. All the actual processes are irreversible processes. However, as an engineering graduate, okay, or as an engineer who is working in the field, our aim should be to decrease the irreversibility. Our aim should be to decrease the irreversibility, right? And how to decrease the irreversibility, that we need to understand it with the help of the concept of exergy, right? So here I will be considering a special case of irreversibility, that is irreversible heat transfer. Okay, irreversible heat transfer. I am going to show you that if the heat transfer is irreversible, then that leads to the destruction in exergy. That leads to the destruction in exergy, or that leads to the decrease in the exergy, decrease in the available energy. So let me ask you this question, that what do you understand by irreversible heat transfer? What do you understand by irreversible heat transfer? I want you to answer. It would be better if others also answer, apart from the students who are regularly answering. It would be nice if others also chip in and they try to give me this answer, that what do you understand by irreversible heat transfer? Irreversible heat transfer. I'm going to show you that irreversible heat transfer. Yeah, Gunjan is right. Gunjan is right. I want you to appreciate that irreversible heat transfer leads to exergy destruction, decrease in available energy, decrease in exergy. Okay, so Gunjan is right. Huge temperature difference between what and what? Gunjan. Gunjan, huge temperature difference between what and what? And what is the meaning of reversible heat transfer? And what is the meaning of reversible heat transfer? Anybody? Because this is a central concept. Okay, Gargi has typed up the answer. Tejas is saying equivalent to exergy destroyed. No, Tejas, that is okay, but what is the meaning of irreversible heat transfer? Irreversible heat transfer leads to exergy destruction. Okay, but what is that? Okay, Gunjan is saying temperature difference between source and sink. No, no, Gunjan, that is incorrect. It is not the temperature difference between source and sink. Between the two interacting bodies, right? Correct. Gargi is right. Anybody? Okay, let me explain you this. Yeah, Neha is right. But finite temperature difference between what and what? Neha. Kunal, in reversible absorbs heat Q1. No, 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 no. No, Kunal, that is not the case. In reversible as well as irreversible, the heat transfer would be the same. That is not the issue. Kunal, that is not the issue. Neha is saying between two bodies. Okay. Okay, let me answer this. When I'm saying there is an irreversible heat transfer, okay, as many of you have said correctly, the temperature difference between the bodies, the source and the body which is accepting the heat, okay, that temperature difference is finite. That temperature difference is finite. Okay. If the temperature difference is extremely small, negligible, okay, if the temperature difference is negligible, then we say it is almost a reversible heat transfer. Almost a reversible heat transfer. Okay. So now we would be discussing that what is so wrong about irreversible heat transfer. Let us talk about two cases for you to appreciate, and I will be asking you a question. Suppose, okay, take these two cases. I'm using a black now. Okay. Suppose there is a source at 1000 Kelvin. Source is at 1000 Kelvin. Okay. There is other source which is at 1000 Kelvin again. Okay. And this source is transferring the heat, let us say, to the water which is boiling in the boiler. Okay, yesterday you had a discussion on what is a boiler. Okay, so water in the boiler which is boiling at, let us say 1000 Kelvin, and here you have another case where the water is boiling. This is at almost 1000 Kelvin at 900 Kelvin. 900 Kelvin. Okay. Let us say that the heat transfer in this case is 500 kilojoules. and here also the heat transfer is 500 kilojoules. So let me ask you the question that this is case 1, this is case 2. Okay, so whether there is a heat loss in case 2, okay, as compared to case 1, whether there is a heat loss in case 2 as compared to case 1, yes or no, yes or no. I hope you got the question. The question is very simple, that the source is at 1000 Kelvin and there is a heat transfer of 500 kilojoules to water. The second case is the source is at 1000 Kelvin and there is a heat transfer of 500 kilojoules to water. Okay. My question is whether there is a heat loss in case 2 as compared to the case 1. Whether there is a heat loss in the case 2 as compared to the case 1. Okay, Garge is saying yes. Kunal is saying yes. Tanaya is saying yes. Nikhil is saying yes. Samir says yes. Vinay says yes. Ganesh is saying yes. Yes. So many people saying yes. Akanksha, all of you are saying yes, but all of you are wrong. The answer is no. The answer is no. Saurabh, Roshan, Gunjan, Pavan, Saurabh, Dadav, Akanksha, Saunke, Yash More, Vinay Shinde, Samir. The answer is no. You see that in case 1, the heat transfer is 500 kilojoules. In case 2, the heat transfer is 500 kilojoules. In both the cases, there is no heat loss. In both the cases, there is no heat loss. Heat loss is 0 in case 1. Heat loss is 0 in case 2. Are you getting the point? Heat loss is 0 in case 1. Heat loss is 0 in case 2. So what has happened? What has happened in case 2 is that there is no heat loss. There is exergy loss. Exergy destruction is the correct word. There is an exergy destruction in case 2, whereas there is no exergy destruction in case 1. Okay, let me explain you this. Let me explain you this by calculating this. Okay, let me explain you this by calculating this. So calculate the exergy in case 1 and calculate the exergy in case 2. Calculate the exergy of the water. Okay, calculate the exergy of the water in case 1 and exergy of the water in case 2. I want you to calculate the exergy of water in case 1 and exergy of water in case 2. Assume the dead state temperature to be 300 Kelvin. Assume the dead state temperature to be 300 Kelvin. 300 Kelvin. So case 1, the exergy would be Q into 1 minus T naught by T. And case 2, the exergy would be, I am talking about the exergy of the water. Okay, exergy of the water would be Q 1 minus T naught by T dash. Okay, so this is 500 kilojoules. 1 minus 300 upon 1000. Okay, and this is 500 into 1 minus 300 upon 900. So tell me the answer 1 and answer 2. What is the value? What is the value? Calculate using your calculators and tell me the numbers. Now it's simply a question of mathematics. It has nothing to do with concepts as such. So you just calculate fast and tell me the answer in case 1 and case 2. Case 1 and case 2. Okay, so Tejas, Nikhil, they have said that first case it is 350 and second case this goes, so it is 0.775 ja, so around 350 kilojoules, and case 2 it is around 333. Case 2 is what? 333. Okay. Right? Right? Okay. Yugandhara is right. So what does that mean? That is correct. This is just a calculation. What you understand from this, Yugandhara? What do you understand from this? Neha, Tejas, Samir. What do you understand from this? Whether there is a heat loss in case 1 or case 2, there is no heat loss. Okay, there is no heat loss in case 1 and case 2. Then what has been lost and why it has been lost? What has been lost and why it has been lost? Yes. So exergy has been lost. Okay, exergy has been lost, and this has been lost because of finite temperature difference. Finite temperature difference. In case 1, you see that the working fluid, that is water in our case, and the source are at the same temperature. Case 1. So case 1 is a case of reversible heat transfer. Case 1 is a case of reversible heat transfer, whereas case 2 is a case of irreversible heat transfer. So because of irreversible heat transfer, what you find is that the exergy has been destroyed from 350 kilojoules to 330 kilojoules. Okay, there is a decrease in available energy from 350 kilojoules to 333 kilojoules. Means about 20 kilojoules of exergy. 20 kilojoules of exergy has been lost. Okay, destroyed. And why is that exergy destroyed? The exergy has been destroyed because of irreversible heat transfer. Because of irreversible heat transfer. Now suppose, yeah, correct. That is correct, Tanaya. Now suppose you increase the irreversibility. You increase the irreversibility. Okay. So how do I increase the irreversibility? Suppose I want to increase the irreversibility. Okay. So how do I increase the irreversibility? Suppose case 3 you consider where there is more irreversibility. So more irreversibility means, let us say case 3. Okay, let me write down the case 3. Suppose you take case 3. Okay, case 3 wherein there is a source again at 1000 kilojoules. Okay, it is transferring the heat, which is the same heat quantity, please note. And let us say that this water, which is now boiled at 500 Kelvin, at 500 Kelvin. Okay, so what has happened in this case? Case 1, what was the delta T? Delta T between the source and the working fluid. Case 2, what was the delta T? Delta T1, I would say, delta T2, case 2. And what is the delta T in case 3? So in the case 1, the delta T was 0. That is which delta T? Delta T between the working fluid and the source. Working fluid and the source. Okay. The water which is boiling and the source, that temperature difference is 0 in case 1. So the case 1 is a reversible heat transfer. Case 2, the delta T was 100 Kelvin. Okay. So it means it is an irreversible heat transfer. Irreversible heat transfer. And case 3, how much is the delta 3? It is 500 Kelvin. So which is more irreversible, case 2 or case 3? Which is more irreversible, case 2 or case 3? Gunjan, which is more irreversible, case 2 or case 3? Okay, Tejas, Gargi, you are right. Nikhil, you are right. Neha, you are right. Now Samir is right. So case 3 is more irreversible. Now you calculate the exergy in the case 3. Calculate, Tanaya, you are right. Calculate the exergy in the case 3. So how do you calculate the exergy in the case 3? So for that, let me again write down the expression. So exergy would be one minus T naught by T double dash now upon into Q. So 1 minus, let's the temperature I am taking it as 300 upon 500, and the heat transfer is 500 kilojoules. Okay. So this becomes 250 kilojoules. Okay. So what was the exergy in case 1? What was the exergy in case 1? Exergy in case 1 was how much? 350 kilojoules. Exergy in case 2 was how much? 333 kilojoules. And in case 3 we have 250 kilojoules. Okay, so what you should appreciate now that the energy is the same. The energy is the same in all the 3 cases, 500 kilojoules. However, because of irreversible heat transfer, that is the decrease in available energy. There is a decrease in available energy. I hope this is very clear to you now. Okay. I hope this is clear to you. And let me now show you the proof for this. Or I guess that any doubts regarding this before I begin with the proof? Proof I would cover in the next class, but I want you to ask doubt if you have any doubt regarding this. With the help of illustrations, I have shown what I have shown is that if there is a irreversible heat transfer, that leads to exergy destruction, that leads to decrease in available energy. Okay, that leads to decrease in available energy. Ganesh, calculation चुक लगा? 3 by 5, 2 by 5. Okay, 200. Okay, right. Ganesh, thanks for pointing out. Ganesh, this is. I'll just erase this. Okay. Just Ganesh, thanks for pointing out this correction. So case 3, that is 200 kilojoules. Okay. So Okay. So it is 200 kilojoules. 200 kilojoules. So the point is, if so, our aim should be to design the heat engines. Our aim should be to design the heat engines where. So, what are the practical insights we get from this? Okay. Our aim should be to design the heat engine such that the working fluid of that heat engine accepts the heat at a temperature which is closer to the temperature of the source. For example, if you talk about boiler, then and suppose the flue gases in the boiler are at 1000 Kelvin, then we need to make the water boil at closer to 1000 Kelvin. Okay, that is what is the insight. So why is that important? That is important because the work potential of the heat would be decreased as the temperature is decreased. Okay, as the temperature is decreased. So the exergy or the maximum work potential is obtainable if the heat is of highest grade. And when is the heat is of highest grade? When it is of higher temperature, right? So what you can conclude from this is, if you are having a heat of 500 kilojoules, okay, which is at 1000 Kelvin. Sorry, this is Kelvin, not 1000, which is at 1000 Kelvin, right? And if you have a heat of 500 kilojoules, which is at uh, uh, let us say 900 Kelvin, then the heat which is at 900 Kelvin is of better quality than heat which is at 500 Kelvin. Okay, so the heat which is at 1000 Kelvin is better than the heat which is at 900 Kelvin. The heat which is at 900 Kelvin is of better quality than the heat which is at 500 Kelvin. Okay, so the quality aspect of energy is quantified by the term which is the exergy. I hope this is very clear to you. And in the next class, I will derive an expression. The expression has already been derived in the video which has been shared by Professor Murukar. Okay, so in that video, you would see the derivation, which I will be taking again in the next class, where I would show that because of irreversible heat transfer, that is because of the heat transfer to the finite temperature difference, there is the decrease in available energy, or in other words, there is an increase in the unavailable energy. Okay, so with this, I end this webinar for today. Have a good day. Thank you very much. I hope you have enjoyed this lecture. Have a good day.